Did you know that what used to take a big supercomputing cluster, 50 milliseconds, to process just one bit of info from an AI model, well, now it can be done in under 2 milliseconds on a single rack system.
Yeah, it's not just faster, right? It's a completely different scale. It's a monumental shift in how we're building AI, interacting with it, maybe even how we think about it.
It really feels like it.
And this huge leap, it's really driven by a new generation of hardware. Hardware that's, purpose-built, meticulously designed for the incredible demands of modern AI.
Which brings us to today. You've handed us this fascinating stack of sources, everything from super technical specs to what the industry is saying, the reactions.
Right.
And our mission on this deep dive is to unpack NVIDIA's Blackwell B200 and the Grace-Blackwell GB200 superchips. These are being called the engines, powering a whole new industrial revolution in AI. Big words.
Very big words.
So we'll explore what makes them so revolutionary, what they actually mean for the future of AI, and honestly, why everyone from the tech giants down to tiny startups seems to be scrambling to get their hands on them.
Yeah, the demand is pretty intense.
So get ready to really understand what's going on with this pivotal tech. Okay, so let's unpack this for everyone listening. What exactly are these Blackwell chips? And why is NVIDIA using that phrase, the engine to power the new industrial revolution? It's quite a claim.
It is a bold claim, absolutely. But it's rooted in some pretty significant technological steps forward. At its core, Blackwell is NVIDIA's newest GPU architecture.
Okay.
It's the direct successor to the Hopper generation, which was, very successful back in 2022.
Right, H100s, everyone wanted those.
Exactly. And Blackwell, it's named after David Harold Blackwell, a brilliant American mathematician, which kind of signals its foundational importance,
Okay, makes sense.
And the B200 itself, that's the most advanced tensor core GPU they've ever made. It's explicitly designed for AI. For the unique ways these complex AI models compute things, it's not just a small improvement. It feels like they've reimagined what an AI accelerator needs to be.
And then you've got the GD200. That Grace name pops up. What's the Grace part of Grace-Blackwell? Why combine them?
Right, and that's where it gets really interesting. It really highlights a shift in strategy, I think. The GB200 superchip, it's this powerhouse combination.
Right.
It fuses two of those B200 GPUs we just talked about.
Two, wow.
Two, with NVIDIA's high-performance ARM data center CPU, which they call Grace, all inside one single, incredibly powerful module.
Okay, so CPU and GPUs living together.
Yeah, exactly. And they're tightly coupled. There's this blazing fast interconnect between them, 900 gigabytes per second, using something called NVLink C2C.
900 GPUs, just between the CPU and the GPUs.
Yeah, and that super fast direct connection is designed specifically to kill those data bottlenecks you often see in AI workloads.
Getting the data to the GPUs fast enough.
Precisely. Making sure the GPUs are constantly fed, constantly working, not waiting around. Historically, that CPU to GPU communication could really slow things down.
Right.
But here, the Grace CPU is right there, integrated, serving the Blackwell GPUs optimally.
So it's less about making individual parts faster and more about designing this whole integrated system where the CPU and GPU are like a perfectly synchronized team. Is that the key idea?
That's exactly it. It's about building a holistic system where every piece is optimized for AI. These chips are purpose-built for the huge scale of modern generative AI models. We're talking models with hundreds of billions, even trillions of parameters.
Trillions?
Yeah. And these chips promise to let organizations run those huge LLMs, the large language models, in real time, with speed and efficiency that just wasn't possible before.
Because the older generations, like Hopper.
Well, Hopper was powerful, no doubt, but it wasn't really designed with this multi-trillion parameter scale explicitly in mind. You'd often hit limits memory, interconnect bandwidth, or just efficiently handling the specific math these giant models need. Blackwell is really designed to smash through those ceilings.
Okay, so when we talk about performance gains, what does that actually mean in practical terms? If I'm trying to run or train one of these huge AI models, what kind of difference are we really talking about?
We're talking massive gains. Some of the numbers are honestly eye-watering. The B200 GPU on its own is just an engineering marvel.
Right.
It's packed with over 208 billion transistors, which makes it, by many counts, the most complex chip ever built.
208 billion. Wow.
It's built on a custom 4-nanometer process from TSMC. And here's the really clever part. It uses two interconnected silicon dies.
Two separate pieces of silicon.
Yeah, basically. Each one pushed right to the edge of how big you can physically make a single chip, that's called the reticle limit, and then they tie these two halves together with an incredible 10 terabytes per second link.
Wait, 10 terabytes per second? Just between the two halves of one GPU.
10 terabytes per second internal communication.
I can't even picture that speed. It's like moving hundreds, maybe thousands of 4K movies every single second just inside that tiny chip space.
It's almost unimaginable, right? And that incredible internal bandwidth is what lets these two huge silicon dies act like one single seamless monster GPU. It gets rid of the bottlenecks you'd normally expect with a multi-chip design.
Okay, so that translates to
A huge jump in raw compute power and also memory bandwidth, which means these Blackwell systems can not only train multi-trillion parameter models, but also run inference on them.
inference, meaning like getting answers from the already trained model.
Exactly. Doing it in real time. Like the most advanced GPT-style LLMs or those complex mixture of experts networks people are building. Previous generations, like Hopper, they just struggled to do that efficiently. They'd hit bottlenecks that made these massive models either impractical or just way too expensive to run.
So this isn't just, oh, it's 20% faster. This is like enabling things that were basically impossible or just laboratory experiments before, making them actually usable in the real world, in real time.
That's the heart of it. It redefines the scale of problems AI can tackle. It pushes the boundary of what's computationally feasible for AI right now. #2. The technical innovations driving AI acceleration. #A. Massive multi-die GPU design.
You mentioned that 208 billion transistors using that dual die design.
Yeah.
How does that chiplet approach, as you called it, actually work? How does it get around the limits of making one single giant chip?
Right, so the B200 uses this chiplet, or dual die design. The basic problem is trying to make one single enormous piece of silicon gets incredibly difficult and expensive.
Yields probably plummet, right? More
Right.
chances for defects.
Exactly. The bigger the single piece, the higher the chance something goes wrong during manufacturing. So NVIDIA did something ingenious. They took two pieces of silicon, each one basically as large as you can reliably make within that reticle size limit we talked about.
Okay, two max-size pieces.
And then they fused them together seamlessly using that ultra-high-speed 10 terabyte per second NVLink C2C interconnect.
That internal highway again?
Yeah, and this effectively creates one giant logical GPU from two physical components. It allows them to vastly increase the number of cores, the memory channels, the overall compute density, way beyond what you could ever achieve with a single monolithic die. It's kind of like linking two powerful engines so they act as one, perfectly synchronized. #BB, second generation transformer engine, and FP4 precision.
We hear so much about transformer models and LLMs being the foundation of all this new AI stuff. How does Blackwell specifically help those? Beyond just being faster, does it change how the models actually run on the chip?
It does. Blackwell has an upgraded second-generation Tensor Core engine, and it's specifically tailored for these transformer models, which, you're right, are the backbone of today's LLMs.
Okay, so specialized hardware for transformers.
Exactly. But what's really fascinating here, and maybe a bit controversial, but definitely a game changer for inference, is its introduction of native support for 4-bit floating point precision, FP4.
4-bit, FP4, wow. Models often train at 16-bit, maybe 32-bit. Even 8-bit seemed like a big step. Doesn't 4-bit mean you lose a ton of accuracy? Isn't that risky for the AI's output?
That's the immediate reaction, right. And it's a great question. Moving to lower precision like FP8, 8-bit, already saves memory and speeds things up. FP4 cuts that in half again. It's a bold move.
So how do they avoid messing up the results?
Well, NVIDIA has developed some pretty advanced techniques, things they call micro-tensor microscaling and dynamic range management. Essentially, these are smart algorithms and hardware features that let the model operate at this incredibly low precision without actually sacrificing the accuracy in the final answer.
Okay. So it's like intelligently managing the precision where it matters most.
Kind of, yeah. It allows them to maintain fidelity while reaping the huge benefits of FP4. And in practice, this means Blackwell can effectively double the size of the model it can run within a given amount of memory.
Double the model size just from using FP4.
Effectively, yes. Or run the same size model much faster, or using less energy. It means they can efficiently execute or fine-tune models with up to 10 trillion parameters.
10 trillion. That number just sounds unreal.
It was practically impossible before, mostly due to memory constraints and the compute needed. So these new tensor cores, combined with updated software like their TensorRT LLM compiler, they drastically boost the throughput, especially when you're just running inference, getting answers from these giant models. It lets them deliver responses incredibly quickly and efficiently. Hashtag C, 5th generation NVLink and NVSwitch for hyperscale AI.
Okay, that FP4 is incredible for a single chip. But like you said, AI often needs dozens, hundreds, even thousands of these working together in these huge AI factories. How do they all talk to each other without creating a massive traffic jam? Isn't communication between chips often the real bottleneck?
You've hit on a critical point. It absolutely can be. And that's exactly where the 5th generation NVLink and the NVSwitch system come in. It's all about communication at scale.
Okay, NVLink 5, what does that do?
So each individual Blackwell GPU supports an incredible 1.8 terabytes per second of bidirectional bandwidth using this NVLink 5.
1.8 TBs per GPU, just for talking to other GPUs.
Per GPU.
Yeah.
And this is absolutely critical for scaling out these AI workloads. It allows up to 576 GPUs to be connected together in a single high-speed cluster. They can share data and coordinate work incredibly fast, effectively appearing to the software like one single enormous unified GPU.
576 GPUs acting as one. So that sounds less like a cluster and more like a single colossal brain, dissolving the boundaries between the physical chips.
That's a great way to put it. And it's not just the direct GPU to GPU links. The NVLink switch system, especially when you look at their rack scale deployments like the NVL72, that takes it even further.
The NVL72 rack, what does that add?
That system provides an unprecedented 130 terabytes per second of all-to-all GPU communication within that single rack.
130 TBs all-to-all, meaning any GPU can talk to any other GPU at full speed?
Essentially, yes, within that rack. This lets dozens of Blackwell GPU 72, in the case of the NVL72, work together in perfect unison as if they were one giant super GPU. This massively accelerates the training of huge models because training involves constant communication and synchronization between GPUs. And crucially, it enables really fast inference for those mixture of experts models we mentioned.
Ah, the MOE models.
Yeah.
Remind us why interconnect is so key for them.
Right. Mixture of experts models work by having many specialized expert subnetworks. For any given input, only a few relevant experts are activated. But figuring out which experts to use and routing the data requires incredibly fast communication across all the GPUs hosting those experts. Blackwell's interconnect makes that feasible at scale. It's a key enabler for handling these trillion parameter models without communication bottlenecks crippling performance. Hashtag India. Advanced memory and data engines.
Okay, processing power.check, communication.check. But what about feeding these incredibly hungry GPUs with data? AI models need just vast amounts of data constantly. Isn't getting that data to the processors often the real holdup in complex workflows?
You're absolutely right. Even the world's fastest processor is useless if it's just sitting there, starved for data. So first off, Blackwell GPUs come with significantly higher memory bandwidth. We're talking over 3 terabytes per second per GPU in the B200 system.
3 TBs of memory bandwidth per GPU.
Yeah, just constantly feeding those tensor cores. But here's another innovation that's fascinating and maybe a bit overlooked sometimes. They've added a dedicated data decompression engine right onto the chip.
A hardware accelerator just for decompressing data. Why is that such a big deal? Seems like a detail, but I bet it's important.
It's hugely important because in the real world, data isn't just sitting there ready to be used. It's often stored in compressed formats in databases, in large data sets. Retrieving and decompressing that data on the fly can become a major I/O bottleneck.
Meaning the GPUs are waiting for data instead of computing?
Exactly. This dedicated engine basically bypasses that bottleneck. It handles the decompression incredibly quickly right there on the chip. Early numbers suggest something like an 18x faster database query processing on Blackwell systems compared to just using a high-end CPU for that task.
18 times faster just for getting the data ready.
Largely thanks to this engine working together with that high bandwidth memory, HBM3E in this case. It's part of NVIDIA's broader push to accelerate the entire data pipeline on the GPU, not just the core AI math. You accelerate the data prep, the analytics, everything. It's about speeding up the full end-to-end workflow, from raw, stored data to the final AI insight or output. That's vital for real-time AI that needs to interact with huge dynamic data sets constantly. #E, enterprise-grade reliability and security, RAS and confidential computing.
Okay, so we're talking about these massive AI factories, maybe running 247 on thousands of GPUs. What about just keeping them running smoothly? And equally critical, how do you keep all the sensitive data secure? Reliability and security must be absolutely paramount as AI gets baked into core business operations.
Absolutely. This isn't just about speed anymore. It's about making AI genuinely production-ready, enterprise-grade. NVIDIA has built that kind of resilience right into the Blackwell architecture. There's a new RAS engine that stands for Reliability, Availability, Serviceability. This engine continuously monitors the system, and it uses AI-driven predictive analytics to actually forecast potential hardware failures or performance issues before they happen.
So it can predict problems.
That's the goal. This is vital because when you move AI from the lab into mission-critical stuff, think autonomous driving, real-time medical diagnosis, financial fraud detection, even a tiny bit of downtime can be disastrous. Having these robust RAS features baked into the hardware shows a real maturity in AI infrastructure. It lets companies deploy AI with the same confidence they have in their other critical systems.
Makes sense. And for sensitive data, like in healthcare finance, where privacy isn't just nice to have, it's legally required.
Right. Confidential computing features are integrated directly into Blackwell. It natively supports things like encrypting data while it's moving between chips or in memory and other security measures. This ensures that sensitive models and the data they process can be handled with strong privacy protection, even within a large, potentially shared cluster.
So protecting the data and the model itself.
Exactly. It's this holistic approach tackling processing power, memory, the interconnect, reliability, security, even handling specialized AI data formats like FP4 that really makes it possible to run these giant AI models faster, more efficiently, and safely than ever before. It gives businesses the assurances they need for widespread adoption.
Okay, let's talk about that headline number. This 30x faster real-time inference claim for trillion-parameter LLMs. That's just jaw-dropping. It's the kind of number that makes everyone sit up and pay attention. Can you break that down for us? How is that even possible? And what does it actually feel like in an application?
It is an astounding number, right? And it specifically refers to Blackwell's ability to serve up responses from these huge language models in real time, but at a throughput, a rate that dwarfs the previous generation, the Hopper H100 GPU.
Okay, 30x faster than Hopper for this specific task.
For this specific large-scale task, yes. To really get it, imagine talking to an AI assistant. A really smart one that understands complex questions, pulls info from vast data sets, and generates sophisticated, human-like responses.
Like the advanced chatbots we're starting to see.
Exactly. On older platforms, even powerful ones, there might be a noticeable pause, right? A fraction of a second, maybe longer, before the AI replies. With Blackwell, for certain massive models, that delay basically vanishes.
So, instantaneous answers from a trillion-parameter brain.
That's the promise. It means a Blackwell system can generate outputs from a model with over 1 trillion parameters with minimal latency. Older platforms would be way slower, or you'd need a much bigger, much more expensive cluster to even get close, often sacrificing that real-time feel.
So how do they do it? It can't just be clock speed. It feels like a combination of things.
It's absolutely a combination, a symphony, really, of all the innovations we've been discussing working together.
Okay, lay it out.
First, that new FP4 precision we talked about. It dramatically cuts the compute needed while cleverly preserving accuracy. Second, the sheer capacity of the GPU, thanks to that dual die design, basically one super powerful chip. Third, the much faster NVLink scaling, allowing up to 72 GPUs in something like the NVL72 rack to act as one single cohesive unit. And fourth, crucial improvements and optimizations across the entire software stack.
Buffer is key too.
Always. NVIDIA demonstrated that a full GB200 NVL72 rack, that's the one with liquid cooling, linking 36 Grace CPUs and 72 Blackwell GPUs, it behaves like one single massive GPU, specifically tuned to just crush these LLM inference tasks. And in that specific setup, running a 1.8 trillion parameter model, Blackwell delivered 30 times the throughput of a comparable H100 system. While crucially maintaining a very tight latency budget, the delay has to be minimal for real-time interaction.
So give us the numbers again, milliseconds.
What used to take a large H100 cluster, around 50 milliseconds per token per word or part of a word generated, can now be done in under 2 milliseconds on an equivalent Blackwell setup.
50 meters down to under 2 meters. That's the difference between noticeable lag and feeling instantaneous.
Exactly. It makes the interaction feel much more natural, much more fluid. It really opens the door to new kinds of human-AI collaboration that just weren't practical before because of that slight delay. Hashtag tag BB. Context and nuance of the 30x claim.
Okay, that 30x number is incredibly impressive, almost hard to believe. But for our listeners, try and get the real picture. Is that 30x gain the case for every scenario? Or are there important nuances here? When do you see that kind of leap?
That's a very important clarification for a deep dive like this. And yes, it's worth stressing that the 30x figure represents a best-case, very large-scale scenario.
The hero number.
The hero number, exactly. NVIDIA's own footnotes point out this was measured on a very large cluster, and specifically with that huge 1.8 trillion parameter mixture of experts model.
Okay, so not your average model size.
Not yet, anyway. Industry analysis helps clarify this, too. For more typical deployments, maybe smaller models, say a 70 billion parameter LLM, or systems using fewer GPUs, the speed up, while still significant, will be lower. Often more in the range of 8 to 10 times faster inference compared to Hopper for many common real-world use cases.
Okay, so 8-10x for more common scenarios.
Yeah.
Which is still huge.
Absolutely huge. An 8-10x gain is transformative in itself. Think about it. A response that took 1 second now takes maybe 0.1 seconds. Or a single Blackwell GPU can handle the workload that used to require 8 or 10 Hopper GPUs.
All right, that changes the economics completely.
Totally. It means much smoother AI services, chatbots that feel instantly responsive, generative tools for creating images or code that react immediately. It leads to a vastly better user experience across the board. It's not just about the peak number. It's about lifting the performance baseline significantly for everyone.
Makes sense. And what about training these models? That's the other massive compute cost, often taking weeks or months. Any gains there?
Yes. NVIDIA also claims about 4x faster training throughput for large AI models compared to the H100.
4 times faster training. How do they achieve that?
That comes from a mix of things, too. Using FP8 precision for training that's 8-bit, which offers a good balance between speed and the numerical stability needed during training. Also higher clock speeds, and just more power being delivered to the B200 chip itself. And again, better multi-GPU efficiency because of that faster NVLink communication we discussed. They've optimized that whole training pipeline. And here's another really fascinating aspect. Efficiency. Performance per watt.
The power consumption. Although it's a huge issue with AI.
A massive issue. Blackwell shows marked improvements here. NVIDIA claims it's up to 25 times more power efficient in those large-scale inference tests compared to Hopper.
25x more efficient. How?
It's a combination of the architectural design, the move to FP4 for inference, and critically, the integrated liquid cooling used in systems like the NVL72 rack. Liquid cooling allows the chips to run faster and harder without overheating, paradoxically improving overall efficiency.
Wow. So a Blackwell deployment could potentially slash the electricity bill for running AI inference.
By a huge factor, yes. And that directly tackles one of the biggest concerns as AI models get bigger, the enormous energy use and the associated environmental footprint. These efficiency gains are crucial. They'll significantly impact how widely large-scale AI gets adopted, making it more economically viable and, frankly, more sustainable for a much broader range of companies and applications.
Okay, these chips are clearly powerful, efficient, revolutionary.
Yeah.
But who's actually getting them first? Is it just the absolute biggest tech companies, or is access broadening out quickly?
Well, the industry is moving incredibly fast to get these deployed, both in the cloud and in private data centers. When NVIDIA launched Blackwell, it felt like almost every major cloud provider, every server maker, every AI powerhouse pledged they were adopting it.
So huge demand right out of the gate.
Immense, almost insatiable demand. These are seen as the essential tools for the next wave of AI, and everyone wants in. It's a truly global rollout.
So tell us about the big cloud giants. AWS, Azure, Google Cloud. Are they all on board? Even the ones like Google who have their own custom AI chips.
They are, and the level of collaboration is pretty remarkable. Let's take Amazon AWS. They've worked with NVIDIA for, 13 years now, since the very first cloud GPU instances?
Right, a long partnership.
And it's deep. AWS isn't just putting Blackwell GPUs in their servers. They're co-developing something called Project Seba with NVIDIA.
Project Seba.
Yeah, it integrates these Grace-Blackwell superchips directly with AWS's own Nitro system. That's their custom hardware and software for virtualization and networking. The idea is to create an end-to-end optimized environment specifically for Blackwell. Amazon CEO Andy Jassy was very clear. Their goal is to make AWS the best place for anyone to run NVIDIA GPUs in the cloud.
Okay, deep integration at AWS. What about Microsoft?
Microsoft Azure also announced they're bringing the GB200 Grace-Blackwell chips to their data centers worldwide. This fits their strategy perfectly, offering the latest NVIDIA GPUs, both for their own massive AI products, like Bing AI, the Copilot features in Office.
Right, they use a ton internally.
Exactly. And also for their external Azure customers building their own AI applications. Microsoft CEO Satya Nadella emphasized delivering the most advanced infrastructure to power customers' AI workloads. And right now, that means Blackwell.
Makes sense. And Google, they had their TPUs, their tensor processing units. Are they still embracing Blackwell?
They are, which is maybe the most interesting signal here. Google Cloud, despite heavily investing in their own custom TPUs, is partnering with NVIDIA to offer Blackwell GPUs as well.
So offering both options.
Seems like it. Alphabet CEO Sundar Pichai talked about their long-standing partnership and specifically mentioned bringing Blackwell's capabilities to Google Cloud customers and also to their own researchers at Google DeepMind.
So even Google sees a need for Blackwell alongside their TPUs. Why do you think that is?
It really underscores a key point. Even companies with powerful custom silicon see the immense value in Blackwell, likely for its versatility, its raw performance on certain workloads, and maybe most importantly, the sheer breadth and maturity of NVIDIA's software ecosystem, CODA, the libraries, the tools. It's not always an either decision for these giants. Sometimes it's and. They want the best tool for the job, and often that's still NVIDIA.
Yeah, it's fascinating. Seeing companies known for their own hardware embrace Blackwell really highlights its broad appeal and the power of that whole NVIDIA ecosystem. It's a strong validation of their full-stack approach hardware plus software. #B. Other industry adopters and on-prem deployments.
Okay, so the big three cloud providers are definitely in. Who else is jumping on the Blackwell train? Is it spreading beyond them into other industries or deployment types?
Oh, absolutely. It's definitely broader. It signals this widespread understanding that Blackwell is kind of the next big thing. For instance, Meta, Facebook parent company, they plan to use Blackwell to train their next-gen Llama model.
Llama, the open source model.
Right.
Exactly. Those are hugely influential in the AI research and developer world. Then you have Oracle Cloud. They're collaborating closely with NVIDIA, too. Their CTO, Larry Ellison, specifically mentioned needing an even more powerful engine like Blackwell for their customers doing heavy machine learning and analytics.
Okay, so other cloud players too.
Yep. And then all the major server makers, think Dell Technologies, HPE, Lenovo, they're all integrating Blackwell into their server lineups. This makes it readily available for companies that want to run it on-premise in their own data centers.
Why would a company choose on-prem over cloud for this?
Several reasons. Sometimes it's data sovereignty rules saying data can't leave a specific location. Sometimes it's ultra-low latency needs where even cloud network speeds aren't fast enough. Or specific security requirements, so having on-prem options is crucial.
Gotcha. And what about maybe some less traditional players? Anyone else notable grabbing headlines?
Well, maybe the most prominent and often talked about is Tesla and Elon Musk's other venture, xAI.
Ah, right. Musk is a big NVIDIA customer.
Yeah. A very big one. And he's been very direct, basically saying there's currently nothing better than NVIDIA hardware for AI. Getting that kind of blunt endorsement from someone building massive AI systems for self-driving and now large language models, that carries weight. Seeing adoption across cloud, enterprise, IT, AI labs, even EV companies like Tesla, it just shows the immense broad demand. And NVIDIA is making it easier for those on-prem deployments, too. They're shipping Blackwell in different forms. Their own DGX systems, their pre-built AI supercomputers will have Blackwell versions.
Like the DGX station.
Yeah.
The AI supercomputer on your desk.
Exactly. That one gets Grace-Blackwell, bringing incredible power to individual developers or small teams. Then there are the huge DGX super PODs for building massive AI factorials in your own data center. They even showed off a smaller DGX Spark unit, highlighting how the architecture can scale down, too.
So from desktop to massive scale, when did these actually start shipping? Are they out there now or still mostly pre-orders?
They started shipping. Initial availability was targeted for late 2024, heading into 2025. NVIDIA confirmed on their Q4 2024 earnings call that Blackwell was in full production and shipping during that quarter.
So the first batches are out.
Yeah, the big cloud providers likely got the very first ones. But heading through 2025, we should see a really rapid scale-up. NVIDIA leadership even said they expect to ship more Blackwells than they originally forecast because the demand is just so high. Supply seems to be ramping aggressively. And that NVL72 rack system we mentioned, that's a really interesting model for on-prem. It packs 36 GB200 superchips, 72 GPUs total, into one pre-integrated liquid-cooled rack.
So a company can just buy the whole rack?
Pretty much. Install one of these AI racks, and you instantly get exascale-class compute power internally. And interestingly, NVIDIA contributed the design for this rack to the Open Compute project, OCP.
Why is that significant?
OCP. It helps standardize AI infrastructure, makes it easier for different vendors to build compatible systems, potentially lowering costs and speeding up adoption. So this dual ramp-up widespread availability in the cloud and these powerful standardized on-prem options means developers all over the world will get access to this tech much faster. It's going to accelerate AI projects everywhere. Hashtag #TechBA, viral buzz, and industry reaction. Hashtag tech yay, tech world excitement.
It really feels like Blackwell generated more than just industry interest. It felt like real buzz spilling out beyond the usual tech circles. What was the reaction like from engineers, researchers, the people actually building things with AI?
You're absolutely right. The Blackwell launch created genuine viral-level buzz in tech circles, definitely, but also in the financial community and among developers. I saw one analyst joke that the B200 announcement got more nerd attention than an iPhone launch.
Chuckles. That says something.
Yeah, it really does. It's a testament to how central AI hardware has become. Engineers, AI practitioners, they were glued to the keynotes, poring over the spec sheets. There was real excitement about what these chips unlock.
Like what specifically?
The potential for truly real-time chatbots that don't stumble. The ability to run much larger open source models on maybe more accessible hardware configurations. Opening up new frontiers in scientific research that were just computationally impossible before. You saw social media, forums like Reddit just light up. People intensely discussing the implications of FP4. How to best use the multi-GPU scaling. Practical questions like, okay, could I actually fine-tune a 100 billion parameter model on just one Blackwell node now? Things that sounded like science fiction a year ago.
Right.
And the developer community is especially keen on the improved software stack that comes with it, the updates to CUDA, TensorRT, to NeMo for LLMs. These tools are critical. They hide a lot of the hardware complexity, letting developers actually use all that power without needing a PhD in GPU architecture. Blackwell quickly became the shorthand for next-level AI capabilities. It's the new benchmark. Hashtag #TechB, financial markets and business impact.
And the financial world, you mentioned them. Given NVIDIA's position and this level of excitement, I assume Wall Street paid close attention. How did the markets react?
Oh, absolutely. NVIDIA's stock surged to record highs right around the Blackwell announcements. It briefly became one of the most valuable companies in the world, which is stunning.
Incredible.
Investors clearly saw Blackwell as solidifying, even extending, NVIDIA's already dominant lead in AI chips. And crucially, this happened just as demand for AI compute is absolutely exploding across every industry. It felt like perfect timing. Their CFO, Colette Kress, made headlines during an earnings call when she described the demand for Blackwell as simply staggering. She said they were racing to scale supply to meet the incredible demand.
Staggering. That quote was everywhere.
It was, and it was taken as solid proof that the AI investment boom is far from over. If anything, it's accelerating. Companies everywhere are shifting budgets towards AI initiatives, and Blackwell GPUs became this incredibly sought-after, almost strategic resource overnight.
You saw other companies mentioning it too, right?
Definitely. Cloud providers like Microsoft explicitly cited AI infrastructure, which, let's be honest, largely means NVIDIA GPUs right now as a major focus for their capital spending. It just validated this whole AI gold rush narrative. Some analysts even started calling NVIDIA's AI hardware the new oil, implying it's the essential fuel for the next wave of technological and economic growth. Hashtag she, industry leadership endorsements and broader influence.
It wasn't just the markets either. It seemed like every major tech leader, every top AI researcher had something positive to say about Blackwell. What kind of impact did that sort of unified endorsement have?
It has a huge impact. From a leadership perspective, the reaction was almost universally positive, which is rare. At the launch event itself, you had leaders from top tech firms lining up to praise Blackwell. Well, Demis Hassabis from Google DeepMind lauded its breakthrough technological capabilities for science and AI research. Mark Zuckerberg at Meta talked about being eager to use Blackwell for their next AI products and open models, which is a big deal for the open source community. Sam Altman from OpenAI said it offers massive performance leaps, critical for the kind of cutting-edge models they're building.
Heavy hitters.
Absolutely. Getting those kinds of quotes, plus Elon Musk's very direct approval, it all went viral. It cemented this perception that Blackwell is the premier platform for serious AI right now. Achieving that kind of cross-industry consensus is really unusual and speaks volumes about NVIDIA's position. And it goes beyond just the big tech firms. You see enterprise AI adopters, even governments rallying around NVIDIA's platform. Companies in healthcare are talking about Blackwell for drug discovery, automotive companies for autonomous driving AI, finance for algorithmic trading.
Yeah.
It's embedding itself in roadmaps across sectors.
And governments, too.
Oh, yeah. Globally, there's this push to build national AI capabilities, AI national labs, new supercomputers. And very often, Blackwell is the default hardware choice unless there are specific geopolitical reasons to look elsewhere. And remember that OCP contribution for the NVL72 rack design.
Right, making the rack design open.
That move signals NVIDIA's influence in setting industry-wide standards. They're not just selling chips, they're shaping the entire AI infrastructure landscape.
Okay, NVIDIA clearly has a commanding lead, but they're not the only player in this high-stakes game, right? How does Blackwell stack up against the competition? Let's start with AMD. Their Instinct MI300 series is often seen as the main rival in the data center.
That's right. The competitive landscape is crucial, and AMD is definitely NVIDIA's most significant competitor in this space. Their flagship AI accelerators, like the MI300X and the newer MI325X, are aimed squarely at the same market.
What are AMD's strengths there?
One key advantage for AMD, particularly with the MI300X, has been memory capacity. It offers up to 192 gigabytes of HBM3 memory on a single package.
192 GB on one chip. That's more than the B200, right?
It is, and that's very appealing for running inference on extremely large models, where fitting the entire model into the GPU's memory is a huge benefit for speed and simplicity.
Okay, so AMD might win on memory capacity. What about raw compute performance for AI tasks?
That's where Blackwell seems to maintain the edge. Early benchmarks and analyses suggest that AMD's latest, the MI325X, performs roughly on par with NVIDIA's previous generation H200, which was an interim update to Hopper.
So MI325X is competing with last-gen NVIDIA, implying Blackwell B200 is a step ahead.
That seems to be the consensus, roughly a generational lead for Blackwell in terms of raw AI compute throughput. NVIDIA's Big 30X inference claim, while specific, highlights scenarios like trillion-parameter models where Blackwell's specialized architecture, like FP4 support, and that massive interconnect really gives it an advantage.
So AMD's angle might be more memory and maybe price?
Exactly. Memory capacity is a clear strength. And there are reports suggesting cloud providers can get MI300X chips for significantly less than Blackwell GPUs. So for customers where memory is the absolute priority or who are very cost sensitive, AMD presents a compelling alternative. But while AMD Instinct offers competitive performance, especially if you look at traditional high-performance computing, HPC tasks, or mixed workloads, NVIDIA's Blackwell generally leads in that specialized AI throughput, particularly accelerating transformers. And crucially, NVIDIA's software ecosystem CUD is still miles ahead of AMD's ROCm in terms of developer adoption, tooling, and the sheer number of optimized libraries available.
So the software maturity is still a big NVIDIA advantage.
It's huge. ROCm is improving rapidly, AMD is investing heavily, but CUDA has decades of development and a massive established community behind it. So, bottom line, AMD is narrowing the gap, providing vital competition, especially on price and memory. But Blackwell is still generally seen as the highest performing, most broadly supported option for the absolute cutting edge of AI right now. ###B, Google, TPU-V5, and TPUs in general.
Okay, what about Google? They've been building their own custom AI chips, the TPUs, for years, mainly for their own use. How do those compare to Blackwell? And why is Google still partnering with NVIDIA if they have TPUs?
Right. Google's tensor processing units are a different beast. They're custom ASICs, application-specific integrated circuits, designed primarily for Google's own massive AI services, like Search and Translate, and also offered to some Google Cloud customers.
So highly specialized.
Very specialized. Historically, TPUs have excelled at one thing in particular, matrix multiplication, which is the core mathematical operation in most neural networks. They are incredibly efficient for training large models if those models fit well within Google's preferred framework, TensorFlow, and their specific architectural approach. For Google's own internal scale, TPUs often provide excellent cost performance.
So where does Blackwell have the advantage over TPUs?
Flexibility and generality. NVIDIA GPUs support a much broader range of AI frameworks. PyTorch is hugely popular, JAX, TensorFlow itself, and many others. They're also used for tasks beyond neural networks, like scientific computing, data analytics, simulation.
So TPUs are great for TensorFlow deep learning, but maybe less adaptable?
Generally, yes. They're less flexible for diverse algorithms or custom code that falls outside Google's optimized paths. Also, Blackwell is available in many environments: cloud, on-premise, even edge devices. TPUs are pretty much confined to Google's cloud infrastructure. You can't typically buy them and put them in your own data center.
Which explains why Google might still want Blackwell.
Exactly. It offers versatility for their cloud customers who might prefer PyTorch or have different types of workloads. And even for Google's own researchers at DeepMind, having access to the state-of-the-art NVIDIA platform with its mature ecosystem is valuable for pushing boundaries. It shows that even with excellent custom silicon, there's still a strong case for NVIDIA's general-purpose power and broad software support. ###C. Apple's AI chip, Neural Engine, Apple Intelligence.
Okay, one more big name in chips, Apple. They design amazing silicon for their iPhones and Macs, constantly pushing performance and efficiency. Do they have anything that competes with a data center behemoth like Blackwell?
Apple's approach to AI hardware is completely different. They're focused on an entirely different world. They build accelerators called the Neural Engine into their consumer chips, the A series in iPhones, the M series in Macs.
Right, for on-device AI.
Exactly. These are designed for tasks happening right there on your phone or laptop. Things like image recognition in photos, real-time voice processing for Siri, computational photography, augmented reality features. The absolute top priority for Apple is power efficiency. These chips sip power, maybe a few watts, to maximize battery life.
Whereas
Blackwell is a monster that consumes 700, maybe even 1,000 watts per chip, designed for server racks. It's optimized purely for maximum computational throughput, not battery life. They don't even play in the same league.
So zero direct competition.
None at all. Blackwell targets massive-scale AI in the cloud and enterprise data centers, handling models and datasets that would be unthinkable on a phone. Apple Silicon targets personal AI experiences, focusing on privacy by keeping processing local and enhancing the user experience on their devices. Apple's Neural Engine is brilliant at efficiently running smaller, optimized AI models on your device, but it's simply not designed for training GPT-scale models or running trillion-parameter inference farms. That's squarely Blackwell territory. It really highlights how specialized the AI hardware market is becoming. ###D. Other contenders: Intel Gaudi, Cerebras, AWS Trainium Inferentia, Tesla Dojo.
Besides AMD and Google's internal efforts, are there any other significant players trying to chip away at NVIDIA's dominance in the AI accelerator market? Any unique approaches worth mentioning?
Yeah, there are definitely other interesting players, each tackling a piece of the puzzle. Intel, for example, has its Habana Gaudi line. They're now up to Gaudi 3. Intel's strategy seems focused on offering a competitive price-performance alternative, particularly for AI training.
Are they gaining traction?
They claim some wins, especially in specific cloud deals where cost is a major factor. But generally, their software support and raw performance still seem to lag behind NVIDIA's latest. The ecosystem around Gaudi isn't nearly as mature as CDA yet.
Okay. Anyone else with a really different approach?
Cerebras Systems is fascinating. They take a completely unique approach with their wafer-scale chips. Essentially, they build one gigantic chip, almost the size of a whole silicon wafer, designed to keep massive models entirely within the chip's memory during training.
Wow, a single giant chip.
It's an innovative niche solution, very effective for certain types of ultra-large model training, but maybe less flexible than GPUs for varied tasks. Then you have Amazon again with their in-house chips, AWS Trainium for training, and Inferentia for inference.
Right, AWS building their own silicon too.
It shows their technical capability and their strategic desire to reduce reliance on NVIDIA, especially for cost efficiency on certain common workloads within their own cloud. They provide good value for specific tasks on AWS, but they haven't really dethroned GPUs in terms of overall versatility or cutting-edge performance across the board. Amazon still uses a lot of NVIDIA GPUs for the highest-end demands.
And Tesla's Dojo.
Tesla Dojo is another highly specialized case. It's a supercomputer purpose-built only for training Tesla's autonomous driving AI models. It's not offered commercially. It's purely an internal tool optimized for their specific data and algorithms. So you see a pattern here. Each of these alternatives targets a specific segment or offers a particular advantage, maybe price, maybe memory, maybe extreme specialization. But none so far has managed to match the combination of top-tier performance across diverse AI workloads, the incredibly mature developer ecosystem, and the sheer generality that NVIDIA Blackwell provides.
Which explains NVIDIA's market share.
Exactly. That dominance, often cited as over 80% of the AI chip market, comes from that combination. And Blackwell's launch just raises the bar again. Competitors often find themselves benchmarking against NVIDIA's previous generation. Blackwell forces them to keep playing catch-up or to double down on their specific niche advantages. But more competition is ultimately good. It drives innovation and hopefully brings down costs for everyone in the long run. Hashtag tag tag outro.
Okay, that was a deep dive indeed. So, bringing it all together, what does this all mean for you listening? If you're a learner or developer, just someone curious trying to navigate this incredibly fast-moving AI revolution, what are the key takeaways on Blackwell?
Well, I think the main thing is that NVIDIA's Blackwell chips, the B200 GPU, the Grace-Blackwell GB200 superchip, they really represent a pivotal moment, a step change in AI computing.
More than just an upgrade?
Much more. They bring these unprecedented speed-ups, like we talked about, that potential 30x faster inference, 4x faster training. They introduce genuinely novel capabilities, like practical FP4 precision, that massive multi-GPU scaling. And they do it all with significantly better power efficiency.
And these tackle the real problems.
Exactly. They directly address the critical bottlenecks, compute, memory, communication, power consumption that were holding back the deployment of today's biggest AI models and preventing us from building tomorrow's even larger ones.
It really feels like Blackwell is arriving at the perfect moment. The world seems absolutely hungry for more AI, faster AI, more capable AI.
It really does. Companies want bigger models, models that give faster answers. Scientists need more simulation power to tackle grand challenges in medicine, climate, material science. Even the apps on our phones are starting to integrate sophisticated AI features that need to feel instantaneous to be useful.
And Blackwell enables that.
By dramatically lowering the cost and the latency, the delay of AI inference and training, yes, it makes AI applications practical that felt maybe just out of reach before. Think about assistants that can genuinely run these massive 10 trillion parameter models in real time, or generative AI tools for art or code that are truly interactive, always on, without costing a fortune to run or needing a whole power plant.
And the industry buy-in seems almost total.
It's undeniable. Virtually every major cloud provider, every significant tech firm is on board. AWS, Google, Microsoft, Meta. They're all integrating Blackwell. This ensures that Blackwell-powered AI services are going to be ubiquitous, available to developers and businesses everywhere very soon.
It's rare to see that kind of alignment.
It is. The excitement cuts across the board, from CEOs planning strategic investments down to engineers in the trenches building the next AI breakthrough. There's this shared vision that this hardware unlocks fundamentally new possibilities. And while NVIDIA leads, that competition we discussed is heating up, which is ultimately good news. It will drive innovation even faster and hopefully make powerful AI computing more accessible over time.
It really does feel like a foundational technology for this new age of AI. Almost like how a new generation of CPUs used to define the capabilities of computing eras in the past.
That's a perfect analogy. As NVIDIA's CEO, Jensen Huang, often says, generative AI is the defining technology of our time. And Blackwell, arguably, is the machine built specifically to run it. We can expect to see these superchips powering almost everything significant in AI soon, training the next GPT-level model, powering the AI features in the apps you use daily, driving the research that leads to new scientific discoveries. The era of trillion-parameter AI running in real time isn't science fiction anymore. It's here, and Blackwell is right at the heart of it. So here's a final thought to leave you with. Given Blackwell's ability to run these trillion-parameter models almost instantaneously, how might that fundamentally change the nature of how we interact with AI? Could we move beyond just asking questions and getting answers towards a truly seamless, co-creative intelligence, almost like having an AI partner that anticipates, collaborates, thinks alongside us in real time? What kinds of applications might this unlock in fields we can barely even imagine today? Something to ponder as this technology rolls out.